Differential equation. This chapter is about the differential equation, and easiest differential equation you will see is something like this: dy over dx is equal to x squared, and initial value, let's say 0, 1, something like that is the easiest differential equation you will see. And then the way you solve it is, of course, find the antiderivative on both sides. So you have y is equal to 1/3 x cubed, and then of course you have to pick up this constant. Now, this is known as the general solution, but in order to find that constant c, we plug in this value here, so y should be 1, x is equal to 0, c. Now, so we go back, and then y is equal to 1/3 x cubed plus 1 is known as the particular solution. So this is how the differential equation works, and this is one of the easiest cases. But there are some cases that are not so easy, and that's today's example. Dy over dx is equal to x squared plus y squared minus 1 with the initial condition 0, 0. Now, as you can see, because this thing messes you up on the other side, that y, we cannot just find the antiderivative that easy, right? And I've seen even crazier one in my days, and that is like f of x. I mean, you guys don't have to know this now, but from negative infinity to positive infinity, and then some function, multivariable function, x and y, times, here's f again, the same f, and then dy. Like, how do you, right? How do you even, this is a, in a way, kind of differential equation, integral equation, they say, and here's an f, and here's the f, and then we have to find this f of x as a function. Right? You will never see this probably, but hey. So, but one thing we learned here is the solutions to differential equation is a function. So we are trying to find whatever the function is. This is today's example. This is some probably like upper division, graduate school somewhere in the future. Okay? And we need the initial condition, and we need some kind of derivative expression of generally x and y. Okay? So let's look at this case. This thingy is my example here. It messes you up, so you cannot really solve this differential equation, but there should be a way to do computer simulation. Mission to Mars, maybe you guys heard about that. So let's see how we can do this. Number one idea, this is more of an art than a science, but we can sketch this thingy and then somehow find out roughly what this curve looks like. Okay, so 0, 0, for example, here, once you plug in and you get this coordinate from here and then plug it into our differential equation. So it's dy over dx will be 0 plus 0 minus 1, negative 1. And then one thing you notice is dy over dx is a slope now, isn't it? So we have a slope of negative 1, which looks like that. Let's plug in 1, 0 then. And there's a more efficient way to do this. Methodically, we start from the origin and work our way around the axis first, then around here. So plug in 1, 0 here. 1 squared plus 0 minus 1 is 0. So this slope right there is flat. And 2, 0, once you put 2 here, that's 4 plus 0 minus 1 is 3. So 3 looks about like this. Oh, okay, it's not. Hopefully this computer is not frozen. 3 like that. Now let's try negative 1, 0. Negative 1 here is still positive 1, 0, negative 1. So this is still 0. And that tells you this is 3 now, isn't it? Okay, what about 0, 1? Plug in 0, 1 here. That's 0, which should tell you this is 0. We can do this very efficiently. 0, 2. Here, that's 4 minus 1, 3 again, so this is 3, and this is 3. How about that? Let's try 1, 1. 1 plus 1 minus 1 is positive 1, so it's that way. That also should tell you everything here is positive 1. And then let's try 2, 1. 2 squared, 4, plus 1 minus 1. So slope here is 4, it's steeper. That tells you this is 4. This is 4, this is 4, this is 4, and so is this. How about that, eh? And then now, 2, 2. Once you plug into 2, that's 2 squared plus 2 squared. So we have 8 minus 1, 7. So this is almost vertical. And we can do this very efficiently. Now, let's say this thing has to pass through 0, 0. So then how do we sketch the curve? Think of this as some kind of wind pattern. And then we are releasing tiny particles everywhere. Then it'll fly in this wind. But the particle that happens to go through this point, where does it go? Where is the path of this particle? So we want to make this thing parallel to this field everywhere. And then it'll follow that path. So that happens to be the solution curve. Okay, and we still cannot figure out explicitly what that curve is. But if you go back in time, the other side, it'll be something like this, and then it'll be quite symmetrical, as you can see from the curve. So it'll follow that kind of path. So this is roughly approximating curve of this solution to differential equation. Okay, so far so good. Now, and second way, and there will be a quiz on this, it's called the Oilless method. Okay. Euler's method is a numerical way you can program your computer or calculator, which you'll have to do in this chapter to do this. So here's the theory first. Okay, so when we say limit of delta y over delta x, as delta x approaching 0, that's what we define as dy over dx, our derivative. Meaning for small delta y and delta x, this has to be approximately the same as dy over dx. Okay. Now, that means our delta y increment has to be approximately dy over dx times delta x. Okay. Now, what is dy over dx? Well, we'll use the same example. Dy over dx we just had was x squared plus y squared minus 1. Now you take this and substitute it right there. Then what we get is dy over delta y is approximately equal to x squared plus y squared minus 1 times delta x. Okay. Now you never probably thought about it like that. Okay, with this we can compute a lot of coordinates. Now say the initial condition is still 0, 0. Now the problem also gives you the step size. Let's say it's 0.5. Okay. Once you have this, then we use this formula right here to calculate delta y over delta x. Okay, let's see how that can be done. So we start with xy table like that, and we start with 0, 0 because our initial condition here is 0, 0. Okay. Now, then x increases by 0.5, and that's fixed by the problem because here delta x is 0.5. We just need to compute delta y's. So delta y in this case is approximately equal to, now we are using this formula right here, but we are substituting these coordinates. So we have 0 squared, I'm going to zoom in a little bit, 0 squared plus 0 squared minus 1 times delta x, which is 0.5. And that gives you negative 0.5. So we add that to this 0 y value, so we have negative 0.5. Now let's take a look back at the curve and what that looked like. If we go back up here, see, as x increases by half, how much does y move? Well, negative half-ish. It's not exactly, but this is an the curve is an approximation. Euler's method is an approximation. So move over by half and down by half is somewhat agree. It's like one blind guy leading another one, but they somewhat agree. Now, using this, of course, x will increase by 0.5 again. So we add 0.5, so we have 1.0 here. And we'll calculate delta y again. Delta y approximately now using this coordinate, these two. So we have 0.5 squared plus negative 0.5 squared minus 1 times 0.5. Okay, and that gives you negative 0.25. Okay, now we add that to the y value because that's increment of y, so we have negative 0.75. Let's see if that agrees with our thingy. So we increased another half, and this is about flat, but it's slightly lower than before, right? It's going to lag behind, and I will explain soon why that is the way it is, but it somewhat agrees with our curve, okay? Where I just set up the next one and not really compute, but x will increase by 0.5 again, so it became 1.5, and our delta y, now using these two, so we have 1 squared plus negative 0.75 squared minus 1 and times 0.5, and whatever you get here, you plug it and add it to this value, and then you compute the next one. So this is what's going on. Our curve, as you saw, looks somewhat like this, right? And then let's say this is 0, 0. Okay, what's going on is, remember we used to have a linearization? When we had a linearization, we had an equation of the tangent line like that. Okay, but instead of going all the way after 0.5, this is 0.5. So this is 0.5 and negative 0.5. We compute the slope again. Okay, when we are doing Newton's method, then we go back to the curve, plug it in, and then find the tangent again. But here, actually, we are using this point, and we just compute the slope. And then we are finding another equation, not the tangent, but it's parallel to this curve right there. So it goes off like that. And then let's say this point is our next plot, which is 1 and negative 0.75 is right here. And then we recalculate the slope again, then it'll go off like that. And the next one will go off like that. It has to be parallel to this. So it'll always lag behind the actual curve. And if our step size, delta x, is smaller, then it'll be closer to our curve. Okay. And then question of the, well, under approximation, over approximation comes up. Okay. So whatever the value here will be, so our calculation, Euler's method, here will be below. So it's under approximation, isn't it? Under approximation. And then the reason, explain why. Why is it under approximation? And the reason, it has to do with the concavity of this again, right? So because the curve is concave up everywhere. Well, how can we show it? Let's say we know it because we sketched the slope field, but how can we show it without doing it? This is how. Remember, dy over dx was x squared plus y squared minus 1, correct? Now we can take a and crashed again. Oh, it was doing so well. Okay, hopefully it'll come back, and let me finish this recording. Okay, let's see if it works. Okay, now we want to do second derivative, which tells us the concavity. Well, this one is 2x, this one is 2y, and then of course the chain rule, and then -1 dies. Now, well then what is dy over dx? dy over dx is all of this. Then we can plug that in here again. So our second derivative becomes 2x plus 2y times x squared plus y squared minus 1. Now we have to know whether that is positive or not. Okay, as long as we have any xy value not equal to 0, then you can see we can plug it in and tell whether this is positive or not. And in this case, they all turn out to be positive in all these values. Okay, so this becomes positive. Therefore, we have concave up. And thus, this whole thing is undone. Now, we have to find the antiderivative of this. Okay, well, we have this thingy, which your book claims to be the inverse tangent. Now, your book is, let me just state it. Your book is expecting you to memorize this formula. So this one is the inverse tangent. I told you not to memorize this as a formula, but if you memorize, I wrote x instead of t. Right? If you take a inverse tangent of, derivative of this inverse tangent, you get exactly that. But if you don't recognize it, you're doing the right thing because I told you not to memorize it. So of course you don't recognize it. Okay? I'm going to do that on the side here. Okay? So let's say the derivative, the antiderivative. First thing, what is a nice symbol for antiderivative? We don't have a good symbol for antiderivative. You know what I'm saying? So Leibniz came through again, and according to Leibniz, this is it. Wait, aren't we missing limits of integration a to b, 0 to 1, or whatever? Right? This usually, if you have 0 to 1, this after evaluating, this becomes a number, is a constant. You know what I'm saying? However, we can make it a function by putting 0 to x on top. And that's my favorite, right? You figured that out from chapter 5 test. But, no, we still need and we can say that's an antiderivative, but we just want the antiderivative symbol. And since the integral is same as antiderivative according to fundamental theorem, so Leibniz, he comes through again and he decided to use this as an antiderivative symbol. So it's like a parentheses, a grouping symbol. Anything between this symbol and that symbol without a and b means find the antiderivative of that thing in between. It's our symbol from now on, okay? And then mathematicians love to create new vocab for the same meaning, and that sometimes is called indefinite integral, as opposed to definite integral like 0 to 1, okay? It's just a symbol, okay? So this is our antiderivative symbol from now on. And then what we're going to do is, there's a nice trick. You notice that I say trick, not trick. Is let x to be tangent theta. Okay, now why would I want to do that? Oh, first of all, what happens if you, 1 over thingy, it must be ln, right? What happens if you write such a thing on your test? How many points does that earn? That would be, it's not 0, it's worse than 0, it's negative 10. Don't do it. This is how you get negative 10 points. You've been warned multiple times on the recording. Don't do it. I have a video evidence. Okay, only time you get ln is if this is 1 over t or 1 over x, single power, okay? Having two terms, so let's delete this, God no, right? Having single term is nicer. If this 1 is not there, then this is just t to the negative second power, and then you can use the power rule, right? So this having two terms in the denominator is not nice, and this is my motivation for using trig. This known as a trig substitution. There's a whole section on this later, so don't be afraid. So 1 plus, did I write x again? God. I meant t. Okay, so 1 plus t squared. What does that become? This is 1 plus tangent squared theta now, isn't it? Oh, after the identity quiz, you should recognize that one. According to trig identity, what is that thing equal to? Feel free to use your microphone.
Secant squared.
Secant squared, great, right? So we at least have secant squared here, right? And then we cannot still write dt1. No, we can't do that. Why not? Because this is theta and this is t. Mismatch of the variable. You know what I'm saying? So now we have to go get that dt. How do we get dt? Well, we can take a derivative, dt over the theta. How's that? Because we have t as in terms of theta. So if we do that, what's the derivative of tangent theta? That's secant squared theta again now, isn't it? But we don't want dt over the theta, we just want dt. So let's move the theta over to the other side. After all, you've seen this thing before, right? So replace that dt with this entire thingy. Bang. You know what I'm saying? So I'm gonna write the secant square on the numerator. Secant squared theta, and then the theta. Magic happens. This is so nice. They cancel. So you have this. This is the easiest integral. What are we integrating? Or what are we finding the antiderivative? As a synonymous term, integrate, antiderivative, 1. So what's the antiderivative of 1? That. And then plus c, eh? You cannot leave your answer like that. Why not? Because theta is something that we just created. You know what I'm saying? So we have to go back and remember what that was. Oh, yeah, that's a relationship between t and theta. So theta must be inverse tangent of t. I told you this is inverse tangent right there, that part. You get it? So that's where that thing comes from. And don't worry, I have the entire section on this lesson. So for now, right? What about that one then? Right? Do you remember how to, well, let's remind ourselves. We'll study this. Derivative of, my computer's frozen. Derivative of 2 to the t. When we say study in math, this is it, not read and memorize, that's not studying. Then hopefully it'll shine a light on how to find the antiderivative of such a thing. Because derivative, antiderivative, you know what I'm saying? Opposite operation. So, do you remember forgetting this technique? Chi and E technique? And E can get a little smaller, ln2, and that T comes to the front. Now we can differentiate. So e to the something, derivative is still e to the something. And then chain rule creates this, say yes. Okay, then this e to the thingy was 2 to the t, and then ln2. You with me? Wait a minute. Why does that look familiar? Look at that, right? Ah, so what does that tell you the antiderivative of that thing is? That thing is just 2 to the t now, isn't it? So derivative of something exponential function is always that function times ln of that base. And it works even if it's e to the t, because e to the t, derivative is e to the t, and then ln e is 1. You get it? So antiderivative is just divide by ln of that base. You know what I'm saying? Ah, okay. And then what am I forgetting? One last thing. This thing is a big deal in differential equations, okay? You get at most half, usually about 40% on according to AP grading guideline if you forget C. It's a big deal, and watch why. This part is known as the general solution, okay? This C could be anything, which means it's a bunch of different curves vertically looking identical. You know what I'm saying? We have to pick one according to this initial condition, and that initial condition, I'm going to write it as coordinate form at 0, 3, when t is equal to 0, y is equal to 3. So we plug it in. So on the left-hand side, we get 3. And on the right-hand side, plug in 0. This is 0, right? I'm going to write it the long way. Inverse tangent of 0 plus 2 to the 0 plus c. And you have to be careful. This is 0. This is not 0. This is 1. So that tells you c is equal to 2 now. You with me? Now, then we can say, therefore, our y is equal to inverse tangent of t plus 2. This is our final answer. And watch the video. This is known as the particular solution. This is one particular one that satisfies both this and this. General solution only satisfies this and not that. You get it?